Hello friends, welcome back to my YouTube channel. In this video, I'll be discussing a numerical based on the McCabe Thiele method. This will be 30th part of my discussion on distillation. And this numerical, we will understand how to find the number of equilibrium stages in a typical tray column. And for that, we will be using the McCabe Thiele method. So let us begin the discussion. To start with, first we will know what is the numerical statement. A mixture of 33% mole of A and 67% mole of B is to be separated in a fractionating column. A is the more volatile component in the mixture, in the feed solution. The concentration of E in the distillate is 93% mole and 96% of all E is in the distillate. The feed is half vapor and the reflux ratio is 4:1. How many equilibrium stages are required in each section of the column? That is to be found out. And for that, we will assume the average relative volatility to be 2.51. Okay. So let us first, this is a numerical statement. Now, first of all, we will note down the given things, the given information. What is the given data? As far as the feed is concerned, it is a binary solution of A and B. There are two components, A and B. A is the more volatile component. That means A has a lower boiling point and a higher vapor pressure as compared to that of B. The feed is containing 33% mole of A. So that means in this case, XF is 33 by 100, that is 0.33. So in order to convert percentage into fraction, we have to divide with 100. That's why XF is 33 by 100. That comes out to be 0.33. Is half vapor. Feed is half vapor. That means 50% of the feed is vapor and the remaining 50% is liquid. So this information will be used to know the value of Q. So if it is half vapor, that means it is a mixture of vapor and liquid. That is, it is a partially vaporized feed. And you please remember, in the case of partially vaporized feed, the value of Q is equal to the fraction of liquid in it. So in this case, if it is half vapor, that means the fraction of liquid is 0.5 and that will be Q. So you just remember this thing. So Q is 0.5. Whatever is the fraction of liquid in the case of partially vaporized feed, or a mixture of liquid and vapor, whatever is the fraction of the liquid, that will be Q. The distillate, what information is given regarding the distillate? The concentration of E is 93% mole. That means mole fraction you can get in the distillate. So that is XD is 93 by 100. That comes out to be 0.93. Again, in order to convert percentage into fraction, we will have to divide with 100. The other information regarding distillate is 96% of all A is in the distillate. So whatever A is in the system or whatever A is in the feed, 96% of that A goes into the distillate. So again, this information will be useful for us. You'll come to know. Then the reflux ratio is given to us. Reflux ratio is 4:1. What is reflux ratio? This is ratio of molar flow rates of the reflux stream to the distillate stream. And this is given as 4:1. Which means R is 4. Then the average relative volatility is given to us. The value of average relative volatility is given to us. It is 2.51. That means instead of giving the VLE data, they have given us the average relative volatility, and we are going to use this to find or to generate the BLE data. Okay, so let us that is alpha AB average is given to us, it is 2.51, and what is to be found out? We need to find the number of ideal stages or the number of equilibrium stages, and they have asked us to find number of equilibrium stages in the rectifying section and in the stripping section, and we will also report what is the number of feed plate, or which is the feed plate. Okay, so let us solve this. Okay, so first we need to choose the basis, because we don't know this the molar flow rate of the feed, but we know its composition. In such cases, you can start with assuming a basis, and in this case we will be assuming a basis of 100 kilomoles per hour. F is 100 kilomole per hour. So for this basis we will be doing the calculations. First step is we will calculate dW and xW. So out of the 6 quantities that are associated with this calculation, the other 3 are F, then XF and XT. These are known to us, and we have to calculate the remaining 3, that is D, molar flow rate of the distillate, molar flow rate of the bottom product, and XW, that is mole fraction of E in the bottom product. Okay, so let us start. Now for this, the first information that we will be using is, we know that 96% of all A is in the distillate. How do you represent this mathematically? You will represent it like this: XD into D. XD into D, that is fraction of distillate into total distillate, gives fraction of A in the distillate into total distillate gives A in the distillate. And this A is 96% of A in the feed. How to get A in the feed? Fraction of A in the feed, that is XF, into total feed, that is F. 96% of this is in the distillate. So we get a simple mathematical relationship from this information. XD into D is equal to 0.96 into XF into F. So whatever values are known to us, XD is 0.93, so we will use that value. Then D is not known to us, we are going to calculate it. When that is equal to 0.96 into 0.33, XF is 0.33, that is given to us, into F, which is 100, the basis that we have as it. Okay, so now you can know there is only one unknown in this equation, and that is D. So you can solve the equation to get value of D. So that will be 0.93 into D, that is equal to, the product on the right hand side comes out to be 31.68. So 0.93 into D is equal to 31.68. That is, D is equal to 31.68 divided by 0.93. That gives us D as 34.07 kilomole per hour. Okay, so one of the tasks is completed. We have got the value of D. It is 34.07 kilomole per hour. Okay, next, let us get the other quantities. Before that, I'll erase it. Okay. Now, we will be using steady state total material balance. What is the steady state total material balance? F is equal to D plus W. Now F is known, D is known, the only unknown is W. So you can easily get that. Therefore 100 is equal to 34.07 plus W. That is 100 minus 34.07 is equal to W. That is W is equal to 65.94 kilomole per hour. It would be kilomole per hour, not kilomole per second. W is 65.94 kilomole per hour. So in this way, you get the value of W. Now we are left with XW. So for that, we are going to use steady state material balance for A, which is the more volatile component. So steady state material balance for A, how do you write it? It will be F into XF, that is equal to D into XD plus W into XW. So what quantities are known to us? F is 100 into 0.33 XF, that is equal to 34.07. D we calculated into 0.93 XD, which is given to us, plus 65.94 we just calculated into XW, the quantity that we have to find. So if you simplify it, it will be 33 is equal to 31.68 plus 65.94 into XW. That is 33 minus 31.68 is equal to 65.94 into XW. That is 1.32 is equal to 65.94 into XW. That is 1.32 divided by 65.94 is equal to XW, which gives us XW as 0.02. Okay. So in this way, we have found out all the three unknown quantities. We have got D, 34.07 kilomole per hour. We have got W, 65.94 kilomole per hour. And finally, we have got XW, which is 0.02. Okay. Next, the next step is generation of the VLE data, because VLE data is not given to us. Instead of that, they have given us the value of average relative volatility. So how to generate it? How to generate the VLE data? For that, we will be using this equation. Y is equal to alpha AB X divided by 1 plus alpha AB minus 1 into X. And what will be our approach? We are going to assume different values for X. And by using this equation, we are going to get the corresponding values of Y. What values of X to be assumed? These values should be, or they will be between 0 and 1. So X, the minimum value for X will be 0. The minimum value that you can assume for X is 0 and the maximum value is 1. So you need to assume values between these two limits. And the best or the convenient values that can be used in the calculation, I'll show you. So first we will assume the values of X. So the convenient values are 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and finally 1. So these values for X, they are more convenient to use. Okay, so the task would be, we will be using each of this value of X in this equation to get the corresponding value of Y. So let us start with 0. So Y, if we use 0 for X, so that is 2.51 into 0 divided by 1 plus 2.51 minus 1 into 0, that gives Y as 0. So for X is equal to 0, Y is also equal to 0. For X is equal to 0.1, Y will be 2.51 into 0.1 divided by 1 plus 2.51 minus 1 into 0.1. That gives us Y as 0.2. So for X is equal to 0.1, Y is 0.22. Then for X is equal to 0.2, Y will be 2.51 into 0.2 divided by 1 plus 2.51 minus 1 into 0.2. That comes out to be 0.39. So for X is equal to 0.2, Y is 0.39. Then for X is equal to 0.3, Y will be 2.51 into 0.3 divided by 1 plus 2.51 minus 1 into 0.3, which comes out to be 0.52. So value of Y is 0.5. Then for X is equal to 0.4, Y will be 2.51 into 0.4 divided by 1 plus 2.51 minus 1 into 0.4. That gives us a value of 0.63. So for 0.4, it is 0.63. Then for x is equal to 0.5, y will be 0.72. So for 0.5, it is 0.72. Then for x is equal to 0.6, y will be 0.79. So for 0.6, it is 0.79. Then for y is equal to 0.7, for x is equal to 0.7, y will be 0.85. 0.85. For x is equal to 0.8, y will be equal to 0.91. Then for y is equal to 0.9, for x is equal to 0.9, y will be 0.96. And finally, for x is equal to 0.1, y will also be equal to 1. Okay. So in this way, we assume few values of x between 0 and 0.1, and we calculated the remaining value. We calculated the values of y by using this equation. This is how the equilibrium data, that is VLE data, is to be generated. Vapor liquid equilibrium data is to be generated. And now we are going to use this data to plot the distribution diagram or the equilibrium diagram or the XY plot. Okay, so for that, we are going to use this scale. On x-axis, 1 centimeter is equal to 0.1. On y-axis, 1 centimeter is equal to 0.1. This is the most convenient scale that you can use for doing calculations based on McCabe Thiele method. Okay, so for our on x-axis, we will be plotting small x. What is small x? Mole fraction of A in the liquid phase. What is small y, which we will be plotting on the y-axis? It is mole fraction of A in the vapor phase. Mole fraction of A. Why A? Because A is the more volatile component. I have discussed about this distribution diagram and how to plot the distribution diagram in my earlier videos. You please watch those videos. I'll give a link to relevant videos in the description section of this video. Okay. So first, we need to plot or we need to draw the diagonal line for our reference. So I'm doing that. Diagonal line for our reference. Okay. And when you plot the VLE data that we generated, you'll be getting a curve like this. Those points will be plotted like this. And you are going to get the equilibrium curve like this. Okay, so now we are ready with the equilibrium diagram. We are ready with the distribution diagram. We are ready with the XY plot. Now let us move ahead. First would be, we will be plotting the rectifying section line, operating line for the rectifying section. And for this, we are going to use this information, which is given to us or which is available with us. XD is 0.93. And the other information is, we will be using the intercept made by the rectifying section line on the y-axis. So it is given as XD upon R plus 1. XD is known, R is known. You can easily get the intercept. So intercept will be 0.93 divided by 4 plus 1. That is, intercept is equal to 0.19. Okay. So we are going to use XD, value of XD, which is 0.93, and the value of intercept, which we calculated, and which is 0.19. So first we will locate XD. XD is 0.93. So on this scale, one small division is equal to, you can check, it is 0.02. Okay, so 0.93 will be this first, the small division after 0.9 will be 0.92. And we need 0.93. So 0.93 will be located over here. 0.93 will be located over here. So after locating it, we will go to the diagonal line. Operating line for the rectifying section will start over here. Then let us locate the intercept. Intercept is 0.19. So it will be located at this point. This is 0.18, 0.2. So 0.19 will be located between those two values. So here it will be located 0.19. So now you have this point. You have the starting point for the rectifying section line. Now you can easily draw the rectifying section line. So this is the operating line for the rectifying section. So for plotting it, we have used the value of XD, which is 0.93, and the value of the intercept, which is 0.19. Okay. Now, next is we are supposed to plot the Q line or the feed line. And for this, the information to be used is what is the nature of the feed. Feed is half vapor. And as I said earlier, this being partially vaporized feed, the fraction of liquid in it will be the value of Q. So it is a fraction of liquid in this is 0.5, and that is nothing but Q. So Q comes out to be, or Q is 0.5. Then we need to know the slope of Q line. And how it is given? It is given as Q upon Q minus 1. So therefore slope will be 0.5 divided by 0.5 minus 1. That is, slope will be 0.5 divided by minus 0.5, and it comes out to be minus 1. So here in this case, the Q line is a straight line with negative slope of minus 1. Okay. The other information that we need is the value of XF. XF is 0.33. Okay. So first we will locate XF. So XF will be located over here, 0.32, and then this will be 0.33. Then we will go to the diagonal line. Q line will be starting at this point. Now, in order to plot the Q line, which has a slope of minus 1, we will be using the definition of tan theta. So, well, you must be knowing, I'll show over here. Tan theta, let us say this is the right angle triangle. This is theta. Let this side be m and let this side be n. So as per definition of tan theta is equal to m upon n. Okay, so if n is 1, if value of n is 1, then in that case tan theta will be simply equal to m. I hope you're understanding the concept. So that means if the denominator is made 1, tan theta will be simply equal to numerator. Are you understanding it? So I'm going to use this information. So I now know the Q line is going to start at this point and it has a negative slope. So if that is the case, for a negative slope, I will travel a distance of 1 centimeter or distance equal to 1 length of 1 square in the plot in the left direction. Why in the left direction? Because the slope is negative. So I travel a distance equal to 1 unit. Again, I am using this concept. Tan theta is opposite side divided by adjacent side. And adjacent side, if it is 1, tan theta will be equal to the opposite side. Okay, so if this is 1, now the opposites, the length of the opposite side will be equal to the slope. In this case, slope is 1. So again, I will have to travel a distance of 1 unit in the vertical direction. If, for example, the slope was minus 0.5, for example, I'm saying. So the vertical distance that you have to cover in this case will be 0.5 unit. Are you understanding it? So in this case, slope is minus 1. So that's why I'm covering a distance of 1 unit in the vertical direction. So by doing that, I'm getting this point. Now the Q line of slope minus 1 will be passing through this point and this point. And that will be the Q line. Okay. So here we have used the definition of tan theta. Again, I'll tell you, in this right angle triangle, tan theta is m upon n, and if n is 1, tan theta will be equal to m. So in this, suppose the adjacent side we have made it 1. In that case, slope will be equal to the vertical distance. In this case, it is -1. Since it is -1, we have traveled in the left direction. Had it been positive, you must be traveling in the right direction. And vertically, you need to travel a distance that is equal to the slope. So this is one of the way of plotting a line of the desired slope or required slope. And you can easily follow this method if scale on the y-axis is same as the scale on the x-axis. So you just understand the concept. If you have any doubts, you please mention that in the comment section. So now we are ready with the Q line. We have plotted Q line for a feed which is half Weber. Now let us move ahead. Next, we need to plot the stripping section line. And for plotting stripping section line, we are going to use this information. XW is 0.02. Earlier we calculated this value. So we will locate 0.02. 0.02 will be located over here. Then we will go to the diagonal line. And in that process, we are going to get this point. So the stripping section line will start at this point. At XW is equal to 0.02 on the diagonal. It will be starting at a point on the diagonal whose x coordinate is 0.02. And the line will start at this point and it will pass through the intersection point of Q line and the rectifying section line. Okay, so in this way, you'll be drawing the stripping section line. So this black color line is the stripping section line. This blue line is the rectifying section line. And this, you can say brown line is the feed line or the Q line. Okay, now we are ready with the basic structure. Now we will be plotting the number of stages. We will plot the stages. So for that, we are going to start at this point at XD and then move in a horizontal direction till we reach the equilibrium curve. Once we reach the equilibrium curve, we are going to come down to the rectifying section line. Again, we will be traveling a horizontal distance to reach the equilibrium curve, then to the rectifying section line, horizontally to the equilibrium curve, vertically to the rectifying section line, horizontally to the equilibrium curve, vertically to the rectifying section line, horizontally to the vertical equilibrium curve, vertically to the rectifying section line. And next time when you travel the horizontal distance to reach the equilibrium curve, you are crossing the intersection point of the three lines. So that means next, while going vertically down, you are going to the stripping section line. Once you cross the intersection point of the three lines, vertically you will have to move to the stripping section line. Okay? Then again horizontally to the equilibrium curve, vertically to the stripping section line, horizontally to the equilibrium curve, and then vertically, just a minute. So horizontally to the equilibrium curve, vertically to the stripping section line, horizontally to the equilibrium curve, vertically to the stripping section line, horizontally to the equilibrium curve, vertically to the stripping section line, horizontally to the equilibrium curve, and vertically to the stripping section line. And one more time, when I do, I hope you are able to see this. So next time when I go to the equilibrium curve and come down, I'm crossing this point XW. So that means that will be the last stage, which is nothing but the reboiler in this case. Okay. So in this way, you need to plot, or you have to plot the stages. So you are getting these triangles. By following the procedure, you are actually drawing the triangles, and each triangle, as I said in my earlier video, it is an equilibrium stage. So how many stages will be there? So let us count. So this is stage number 1, stage number 2, stage number 3, stage number 4, stage number 5, stage number 6, stage number 7, stage number 8, stage number 9, stage number 10. This is stage number 11, and the last will be the reboiler. The last stage will actually be reboiler, where concentration is XW. Okay. So in this way, you can find the number of equilibrium stages. Okay. So now our findings. So first we are going to report the number of stages. So number of stages is 11 plus 1 reboiler. So there are 12 stages. 1 out of those 12 is the reboiler. Then stages in the rectifying section, so you can count. So this will be the stages above the one where there is intersection of the 3 lines. So intersection of the 3 lines, you can see it occurs on stage number 6. So the stage before stage number 6 will be in the rectifying section. So in this case, there are 5 stages. 1, 2, 3, 4, and 5. So there are 5 stages in the rectifying section. Then the feed plate will be 6th plate. Why 6th plate? Because in this case, intersection of the 3 lines, it is occurring on 6th plate, or the 6th triangle. So in this case, the feed stage is 6th stage, and the remaining stages will be in the stripping section. So how many stages will be there? 1, 2, 3, 4, 5, and 6. There will be 6 stages in the stripping section. So in this way, you can find the number of stages in a typical tray column. So here, at the end of our discussion, we have reported the total number of stages. Then we have reported how many stages are there in the rectifying section, what is the number of feed plate, and how many stages are there in the stripping section. Okay, so in this way, we can use the McCabe Thiele method to find the number of equilibrium stages in a typical tray column. So with this, I end my discussion for this video. Thanks for watching my video. Please do subscribe to my YouTube channel. Tell your friends to subscribe to it. And if you have any doubts regarding today's discussion or regarding discussion in this video, you please mention that in the comment section. Do like my videos and hit the bell icon so that you will be notified as soon as I upload any new video. Thank you. Thank you for being with me. Have a nice day. Hope to see you soon in my next video.